Howdy, howdy, this is Mr. Potter. In today's lesson, we're going to be talking about compositions of functions. Now, when we compose functions, what we're actually doing is we're putting two functions together. So I want to start off with some ways that we can combine functions. So one way that we can combine two functions, f of x and g of x, is to combine them by adding their components together. And so if I were to take some polynomial like x squared minus 4 and add it to the polynomial 2x plus 3, if I add these component by component, I get x squared plus 2x minus 1. So I can call this a composition of functions by adding them together. And so I can call this function f plus g of x. And so this is one way that I can put two functions together, by adding them component-wise. Another thing that I can do is I could subtract them component-wise, have f minus g of x. And in this case, I would take everything in this first expression, x squared minus 4, and subtract everything in this expression, 2x plus 3. So I'm going to have x squared, which is positive. I'm subtracting a 2x, so that would be negative. And here I've got a negative 4, and here I'll have a negative 3, so that'll actually give me minus 7. Something to keep in mind, though, is that f minus g and g minus f really are different, because in this case I'm taking the 2x plus 3 and subtracting the expression x squared minus 4. So remember, even though addition the order doesn't matter, for subtraction the order does matter, and so these actually end up being two distinct functions. So here I'm going to have 2x plus 3 minus x squared, and then really a plus 4. So I'm going to really have negative x squared plus 2x plus 7. And of course, one of the things that you notice about these two functions is that all they really do is they have the opposite sign. Now, another thing that I can do is I can multiply two functions together. I can talk about f times g at x. In this case, I'm taking the expression x squared plus 4, or excuse me, x squared minus 4, and I'm multiplying it times the expression 2x plus 3. And so this should give me 2x times x squared, or 2x cubed, 2x times negative 4, which is going to be negative 8x. I'm going to have 3 times x squared, so plus 3x squared. And then negative 4 times 3, which would be minus 12. And I can also divide functions. So I can talk about f over g of x. Or I could talk about g over f of x. And the thing you have to watch out here is because division's occurring, we are going to have slight restrictions with our domains. Remember that polynomials have their domain being all real numbers. In other words, from negative infinity to infinity. But because I've got this division going on, I have to watch out and figure out, okay, I've got f on top. I've got g on bottom. And I've got the restriction that x in this case can't be equal to negative 3 halves. If I try and do it the other way, if I have 2x plus 3 over x squared minus 4, my restriction is that x can't be equal to a positive or negative 2. So I do introduce domain restrictions if I do division of polynomials. Of course, any time that the denominator is equal to 0, that's going to introduce restrictions. So if the denominator can never be 0, I won't have a restricted domain necessarily. So it's just something to keep in mind. We can combine these functions by adding or subtracting or multiplying or dividing them with each other. So let's go ahead and advance real quick. So the other thing that we can do is we can talk about true composition of functions. The idea that I can take a function and stick it inside another function. In other words, evaluate f for replacing x with the expression g of x. Now, you'll often see this written as f(og) of x. And also keep in mind, this is not the same thing as the aforementioned multiplication. We actually use a little circle here for of, and this is actually going to put it inside. So what's important for us here is that if I let f of x and g of x be two functions, then we can define the new function f of g of x subject to a new restricted domain. So if I let f of x and g of x be two functions, let's say I've got f of x equal to x squared and g of x being equal to x minus 2, then I can talk about this composition of functions, f of g of x, which I'll write f o g of x. And what this basically means is that everywhere I see x in my f function, I'm going to replace it with this expression. So it's really x minus 2 quantity squared, or x squared minus 4x plus 4. And something to keep in mind is that if either of our functions have an issue with domain, our composition should also have an issue with domain. And that issue with the domain will always include the restrictions for the first two functions, but it may include something else. And so it's just something that we need to keep in mind. So in this case, if I let f of x be x squared, g of x being x minus 2, I can evaluate f of g of x to be this expression. But I could also talk about g of f of x. In other words, g of f at x. In other words, now I'm taking this expression, and everywhere I see an x, I'm replacing it with f. Now, of course, in this case, it's a really simple x squared minus 2. But it certainly could be something more complicated. Now, of course, if we're dealing with polynomials, remember that polynomials have no domain restrictions. So that's nice to know, but keep in mind, polynomials have no domain restrictions. That doesn't mean that other functions don't. So let's say I've got f of x being equal to 1 over x minus 1, g of x being 1 over x minus 2. Now, by the way, keep in mind, x minus 1, my domain restriction is that x can't be equal to 1. Here, my domain restriction is that x can't be equal to 2. So if I'm going to be dealing with the composition of these two functions, then I need to keep that in mind when I'm looking at the composition, that it's going to include these restrictions, but it may also include other restrictions. So now if I evaluate f of g of x, that means that everywhere I see x in my original expression, I've got to replace it with this fraction. So I'm going to have 1 over something minus 1, and that something is x minus 2. Now I'm going to need to simplify this, and probably the easiest way to simplify this is to get a common denominator. So I'm going to have 1 over, my numerator is going to be negative x plus 3 over x minus 2. And of course I've got the reciprocal of a fraction, which means I take the reciprocal of the fraction, x minus 2 over negative x plus 3. Now what you notice is that my domain can't include 1 and it can't include 2, but now I've actually introduced something new here. I actually run into this problem where my denominator can't be 0. I'm not allowed to divide by 0. So that means all of a sudden x equals 3 is also not in my domain. Even though it wasn't a restriction, of our original two functions. And so that's something you need to be aware of. When we're doing a composition of functions, we can introduce other domain restrictions, even though our original function didn't have a domain restriction at that point. So in other words, our domain, in this case, is all x except x equals 1 or 2 or 3. And you can write that in interval notation if you want. You can write it in boundary notation, inequalities, however you feel like writing it. Just realize, though, that composition of functions can introduce a restriction in domain, and it's something that we have to be aware of. Something else you need to be aware of is that we are not necessarily restricted to explicit algebraic functions. I could have a table like this and say let f of x and g of x be defined as this table. And I can figure out what f of g of 1 is by finding out what g of 1 is first. G of 1 is 5, and that 5 is what's going to be substituted into f of x. So this is really equal to whatever f of 5 is, which is 1. If I wanted to find f of g of 2, I'd have to find out what g of 2 is, 4, and then substitute 4 into f of x, which gives me 2. F of g of 3, f of g of 3, well, g of 3 is 3, substituting a 3 gives me 3. F of g of 4, well, I'm going to substitute a 4 in here, which gives me a 3, and f of 3 is 3. And I can do f of g of 5, and substituting a 5 in here gives me a 2. Substituting a 2 in here gives me a 4. So I end up with this functional domain, or this functional definition for f of g of x. And as we mentioned before, I could also evaluate g of f of x. In other words, just by evaluating a number in f first, and then taking the range value and substituting it in for the domain value of g. So I could talk about g of f of 1. And I know that f of 1 is 3. G of 3 is 3. If I do g of f of 2, well, I'm going to substitute 2 and get a 4. Substitute a 4 and get a 3. I could do g of f of 3. Substituting 3 into f gives me 3. Substituting 3 into g gives me 3. So these are all 3 so far. G of f of 4. Well, I'm going to take 4, plug it into f, get 2. Substitute 2 into g and get 4 out of it. And I can do g of f at 5. Substituting a 5 gives me a 1. Substituting a 1 into g gives me a 5. So not only can I do this from an algebraic standpoint, but I can also do this from a tabular standpoint. Given a table of f values and g values, I can do composition of those functions as well. And similarly, I can do it from a graph. So in this case, if I wanted to evaluate f of g of -1, I'm going to need to take a look at g of -1. G is this parabola, and at -1, it has a value of 3. So now I want to know what f of 3 is, and if I go over 1, 2, 3, on the line I'm at -2. If I want to evaluate f of g of 0, I need to look at the parabola at what's happening at 0, and that's at 0, and then substitute f at 0, which gives me 1. F of g of 1, well, I'm going to look at the parabola and see what's happening at 1, and I get -1. And at -1, my line's at -2. Similarly, if I want to evaluate f of g of 2, I'm going to look at my parabola, see what's happening at 2, which is 0. And my line at 0 is +1. That should have been a +2. I don't know why I put a -2. So I'm going to go back 1 and up 2 to get to this point on the line. I'm so sorry about that. Similarly, if I wanted to do g of f at -1, I'm going to substitute -1 into my line first, which is 2. And then I'm going to substitute 2 into my parabola, which gives me 0. G of f of 0? Well, substituting a 0 into my line gives me 1. Substituting 1 into my parabola gives me -1. G of f of 1? is going to give me, well, plugging 1 into my line gives me 0. 0 into my parabola gives me 0. And I can do g of f of 2. Substituting 2 into my line gives me a -1. -1 into my parabola gives me a +3. So what's important to understand is that when I do this composition, when I'm talking about a composition like f of g, or when I'm talking about a composition like g of f, I'm really taking the range of the second function and substituting it as a domain element of the first element. So it's important to understand how to substitute those values, whether we see those values in a functional standpoint, or whether we see those values from a tabular standpoint, or whether we see our values like we did here from a graphical standpoint. So the last thing I want to talk about is what happens when I have one of these composition of functions and I want to find a way to work backwards. In other words, this is my f of g, and I need to know what is f and what is g. Keep in mind that if I'm doing this as f of g of x is my last thing that's being done. So what's the last thing that's being done here? The last thing that's being done is we're taking the square root of something. So I could say that f of something is the square root of something. Well, I can go ahead and say that f of x is just the square root of x. And then g of x is going to be that something. Well, what was b taking the square root of? We were taking the square root of the expression 5 minus x squared. And so this is called decomposition. And one of the things that we will need to do, not only in pre-calculus but in calculus, is given a complicated function, we'll need to decompose it into two functions such that one is a composition of the other. Now, is this the only way I could have done it? Certainly not. I could have said that f of x is the square root of 5 minus something, where that something is x squared. So there's many different ways that we can do this, and sometimes the tricky part is not knowing how to do it, but knowing which one of these we actually want. And so I'm going to finish up with this example here. I've got h of x equals 3 over the square root of x squared plus 6. So one way that I could decompose this is I could say f of x is 3 over something, and that something is the square root of x squared plus 6. I could just as easily said that f of x is equal to 3 over the square root of something, where that something is the expression x squared plus 6. Furthermore, I could have said that f of x is 3 over the square root of something plus 6, where that something is x squared. All of these work out for this h of x, this breaking down of this composition of functions. And it's going to be your job, given a complex function, to break it up into parts that are easier to work with. There isn't necessarily going to be one right answer, but you're going to have to find the answer that works best for the situation that you're in. Once again, this is Mr. Potter. Thank you for watching. Have a great day.